gentlemen, welcome to our second part of our lecture on multiparameter models in STAN. This part will be probably the shortest one, the next one probably also will be short, and the last one will be again a bit longer. Today we will be discussing a more extensive example from the area of political sciences, at least tangentially. Because it will be a survey analysis, so we'll be discussing how to estimate probabilities of election conditional using survey data, and we'll be doing it with very simple multiparameter model, which is the multinomial model for categorical data. Multinomial model is a generalization of a binomial model. This is a model that predicts how many successes or events will happen in certain categories, and its probability distribution is described by a set of parameters theta I, which sum to 1 because they explain the entire space of possible events that can happen. In this case, so each of those events has a probability, and the number of successes is, or the number of events in each category is dependent on the probabilities and a certain number. So we have n events, which n is a sum of y's, and we have our probabilities theta I. So vector y is a vector of counts of observations of each outcome, and thetas are probabilities, and of course in Bayesian context, we are usually interested in estimating the probabilities or predicting possible events. So we'll be interested in the posterior distribution of theta, and we'll be interested in predicted distribution for y's. What is important to see is that there is an conjugate prior for multinomial distribution, and this conjugate prior is the Dirichlet distribution, or Dirichlet, and this distribution gives us probabilities for values of vector theta, and they are parameterized by alpha parameters. This is the same situation as with binomial, where we had a beta distribution, and beta distribution gave us probabilities from theta, and on the other hand, this was very easily interpretable prior, because in case of beta distribution, we could consider values of alpha as previous numbers of successes in certain categories. In case of the Dirichlet distribution and multinomial, it will be number of events occurring in each of the categories. At least we can express this distribution as, and we will get a result which will be again a Dirichlet distribution, like the model will be. So we will be able to get some results from the distribution. However, we won't be doing that. We will be doing that in STAN because of general focus of this course. And this is the part of the theory. So we have a relatively simple distribution depending on number of counts of categories for which we have probabilities, and we have the probability that is for, okay, we have a guess here. So we have our probability distribution defined by our categories, and we have our parameters, and we need to assign prior for them. So this is our theory. We have our model of multinomial model for categorical data, and in case of this model, we are predicting values of how many events happen into each categories, and they are dependent on parameters theta. So our parameters, multiple parameters, are probabilities of each category, which we can assign prior using, for example, Dirichlet distribution. And we will focus on an event for you, most of you listeners, ancient history. So 1988 US presidential election. This was the presidential election where we had our older President Bush, so Bush Senior. Actually not Senior, George H. Bush, the father of George W. Bush, which was most known during the 9/11 crisis in the United States. Again, like this might be ancient history for you, but He was a very important figure at the time, and we have data which is from Gelman's Gelman's book. So during approaching election, CBS News performed a survey in late October of 1988 of 1,447 adults in the United States in order to find out their preferences for upcoming elections. The main candidates were, of course, George H. Bush, who was the Republican Party nominee, and his opponent from Democratic Party was Michael Dukakis. And of course, as always in the United States, you have some number of so-called third-party candidates, which never approach any significant levels, at least not in last 100 years or more of United States elections. So really, we have two candidates. However, from this survey, 727 people have supported George Bush, 583 people supported Dukakis, and 137 gave votes that were either supporting third-party candidates or expressed no opinion. So we start with this very simple model in order to estimate the probabilities of our probabilities that depending on the outcome of the election. So, in order to get the our model will be, we have our data sets of 3 results. We are interested in 3 parameters, so the probabilities of each voting situation. We assume we have a random sampling of our population, so we get, let's say, representative data, which will follow the multinomial distribution, which is the model of our interest. And we are actually interested what is the probability of, or the preference of the population towards George Bush, the actual winner of the election. So we will be interested in the difference between probability of supporting Bush and probability of supporting Dukakis. Because again, as in the United States, we have the first by the post election, so the winner takes all. So we will be focusing on estimating the difference between θ1 and θ2, and we will see how to do that in Stan using generated quantities block. So what we have our data sets. It's a very simple data set, a list consisting of three integers. And again, we start with our normal packages. With one little exception, we are also using the MPL Tern package, which we'll be using for visualization of simplexes, which we'll go to in a moment. And we have the this is one innovation here. So if you would want to repeat this computation here, you will need to install this package, which is relatively without problems. You have a link here under the package name. Additionally, we will be using Avis summary statistics in order to look at results, and we have I have defined certain dictionary of functions that will be used later just for computing median and 90% interval of confidence. So let's start with our model and with our prior predicted distribution. As we know, we are assuming the model of multinomial model, and we assume absolute ignorance about the preference. So our prior will be uniform on the scale. And this, of course, we can again use the formulation similar to beta distribution. In beta distribution, beta of 1, 1 was a uniform distribution, because when assuming as alpha, putting 1s as alpha, then everything will be to the 0 power, and so the probability will be unity. And will be the constant on the entire interval. In the case of the distribution, same situation. Dirichlet distribution with all alphas equal to 1 gives us a uniform distribution of theta. However, there is a one single issue: theta must sum to 1. That's why the data type that we have to use here is not vector with constraints, but a simplex. Simplex is a vector that guarantees that it will be located all its elements will sum to 1, or at least to a constant. In case of geometry, it will be for 3-dimensional, it will be a triangle, and that's why we've installed that extra package, because that package will allow us to visualize the samples from our distribution. At least regarding theta. So we'll be visualizing samples from simplexes, because, as you will see in a moment, it was kind of useful in comparison to marginal distributions. So theta has to be a simplex, so we will have to remember that. We sample it using Dirichlet distribution, which samples on simplexes, so it won't be a problem. And of course, we will be our outputs for prior predictive checks will be sampled using multinomial random number generator. And in our model is general, so we would allow more than 3 categories. We could go for 3, but here we just create a general with k categories and number of votes. And number of votes in this case will be the we will be using how many votes were being cast issue. So we will be observing how the distribution happens. And of course, we can compile this model using our standard methods, and so we'll be sampling it using the following parameters. We will have 3 categories, and we will have as many votes as is in the original data sets. We have some seed, and of course, we have our standard parameters regarding the simulation, because it's only generated quantities model without actual parameters. We use the fixed parameters algorithm in order to get our results. And we'll be doing a bit of magic with our parameters, because for nicer visualization. So this is not that important here what's going on. It's just worth noticing that our fit objects from sampling method can have a method of 2 data frames. So we can transfer our object in our samples into data frames that will allow for visualization. But in this case, I'm not using it directly, just to easily manipulate data, because plotting histograms with pandas directly has certain negative connotations regarding placement of our data. So let's look at the histograms. We generate the histograms of all our variables, and all those variables and our variables of interest will be probabilities theta 1, 2, and 3, and corresponding to them simulated number of outcomes in such category. So as you can see, we have noticed certain behavior. First of all, observing our actual data, which is plotted here with the dashed line, we can see that this data is located inside the interval of possible outcomes. So our model at least allows for results that make sense. Moreover, we can see that our theta parameters are distributed with certain preference towards 0, which might be kind of surprising, because we've discussed that we wanted the uniform probability. But uniform probability for simplexes is not the same as uniform marginal distributions. That's why we can look at the entire distribution samples of theta from our distribution on the simplex. Simplex, as I said, is always triangle, and here we discover something called a trinary plot. Trinary plot puts our values on a grid of triangles, where values of each axis are located as lines going from the vertex. At the vertex is a theta 1 equal to 1. At the bottom is theta 1 equal to 0. So you have the we have the contours of the lines of constant values of theta as horizontal ones. In case of theta 2, one is here, and all the variables are going in lines which are parallel to this edge of the triangle. And finally, from theta 3, we have the parallel lines that going from here. So, as you can see, the same samples that give us these histograms are, well, rather uniformly distributed over our triangle. It's happening that because whenever you approach one values next to different equal to 0, other two has to be divided, has to take the entire sum up to 1. That's why it's very difficult to get values that the values in only values in the middle would give all them the same level. So in order to create the histogram that would give us uniform distribution of all of those would be certainly not uniform in this over the triangular grid. So our model gives us the uniform distribution of our possible vectors, which is not visible at that much on the on our axis. However, it gives us the and so the results are at least allowing for reasonable data. That our data is possible in this context. So our model does not provide us with something that is completely impossible. So this is the first prior check that we did, and this prior check is without much problems. So we can now move to our posterior analysis and our predictions. So let's start with the posterior analysis and create our model for election fit. And our model for election fit is very similar, at least in the data the context. Data is the same as data as similar to the previous, because in order to simulate from the RNG function, we had to provide it with the number of samples. When we are doing the fitting, the number of samples can be computed directly from the vector, because we can sum the numbers of outcomes for each of the categories. So we provide the model with number of categories, and we provide it with the results. So how many votes was in each of the categories. Our parameters is again a simplex of theta, simplex of k-dimension case of 3 variables, and our model is very simple because it just we can ignore the uniform distribution here. We could put here Dirichlet distribution, but because it's uniform in our context, we can just skip it. In case you skip instead the priors for models, it substitutes with uniform distributions. So this is something that we left here, and we don't care about it too much because it's a simplex with a uniform model on simplexes. So it is the generally we are using a stand default. And our model here will be fitting theta in order to our likelihood according with our likelihood, which is multinomial distribution. We supplement it with the generated quantities block. So we will first of all sample the results of the survey. So we will sample the same number of votes, and those number of votes will see how it's distributed with how it's distributed corresponding to our data. Why we are doing it? We are doing it in order to get something that can be called a retrodictive check. So we'll be checking if our model is able to generate our original data, at least in some consistency. So we'll be so we were doing it before. I just didn't call it a retrodictive check before. So we'll be sampling the data, sampling the distribution of possible outcomes, and we'll see if this distribution is corresponding to our original data. And additionally for that, we will be adding the advantage value. The advantage, so how much theta 1 corresponding to George Bush is greater than theta 2 corresponding to the case. So how is the difference positive or negative really? Because if it's positive, then Bush has an advantage. If it's negative, Dukakis has an advantage. So again, we are using our data set. The data set is a dictionary of number of categories and our samples that we've defined earlier, and the model is compiled here, and we are sampling it again with some kind of with a seeding here. So we get our summary for the results. The summary gives us certain information already. We are using the Arvis function summary, which we provided with function dictionary, which is before. We are focusing on variables theta and ysim. We have nice estimates, tight estimates of those values. We will compare it with the histograms in a moment, but our 90% intervals are rather thin, and we have the estimated values, which you can see is rather corresponding to our original data, which we'll see in a moment. Again, some data manipulation magic, and we have our marginal histograms. So, comparing to our previous distribution, we have very nice tight unimodal distributions located at certain values of theta1, theta2, and theta3, and our predicted or retrodictive samples from our model give us a location exactly in the means are exactly in the middle of what we were able to estimate. So getting our getting our posterior located exactly as where we want it. So our retrodictive check is very good. Our model is consistent with the data, and we have our marginal probabilities for each of those those parameters located in our simplex. As you can see, means, if you look at the means add to each other. Here's a 0.5, 0 plus 0.4 plus 0.1, it gives us 1, so it looks nice. And looking at the ternary plot, we can see that samples are very densely located around the intersections of those points. So we don't have tick tails. We see that our theta1 is around 0.5, theta2 is around 0.4, and theta1 is theta3 is around 0.3. So you can see like the values from theta1 are located on this axis, from theta2 are located on this axis, and from theta3 are located on this axis. So this is something that you need to get used to in order to read those plots. But this is, as you can see, we have very nice concentration of samples here. So our model give us location. So what really is left for us to do is to estimate our quantity of interest, so the advantage of theta1 over theta2. So our quantity of interest, so difference between lead, in this case Bush, which is the lead candidate, is theta1, which is minus theta2, and as we can see, all the values in the histograms are positive. So the advantage varies from 0 to 17%, because we can use a percentage scale unit in our histogram, and we can use it for and we can get some like a simple sample analysis, and we can take our samples from our model. So our probability of Dukakis winning will be really the average, the number of points where Dukakis had an advantage. So if the advantage was positive, divided by 4,000. And as we can see from our samples, we had 4,000 samples of 4 Markov chains that sampled for 1,000 of useful samples. We got the 0 number of samples of where this value is negative. So in the context of provided data and our model, probability of Dukakis winning is 0. And if we want to go a step further, we can provide it with certain intervals of probability, so we can get the advantage using our summary statistic function from the Arvis package. So we can limit to advantage variable, and as you can see, The confidence interval is also very positive in here with median of 10%. So really, we're just consistent with the histogram. So what we did here, we took a simple model of the kind. So we had a model on the categorical data with a model of 3 parameters, which were in the form of a simplex. So not a normal vector, but a vector limited to a triangular space in a sense. And using this model, we've sampled both values of parameters from the posterior and values of the predicted outcomes. Predicted outcomes are very well corresponding to original data. We got our confidence intervals for our parameters. We get confidence intervals for our predictions. We can also get the confidence interval for our prediction regarding the advantage of Bush. We can see that the joint probability distribution of theta parameters theta is very densely located in appropriate intersections of values. So it's located around this point of 0.5, 0.4, and 0.1, which is, again, this is a nice visualization useful for only three possible categories. If we have more categories, the visualization are problematic, but here we can still do something. And using samples, we can get additional information, like, for example, the samples of advantage give us the probabilities of Dukakis winning, which are none. And he didn't win, so the model prediction was okay. And this is it for today. So this, I said, this will be our. It was a short video. This model will be again available on GitHub. No dataset is needed. You will get no cached models will be provided, so you'll have to compile it by yourself. And of course, you need to install the Trinary package if you want to do it by yourself. You can try to do some prior information, so you can modify the model for the you can modify the prior model for the posterior and for the prior, for example, assuming certain prior information. So you will see what will happen and how our distribution will go. As again, Dirichlet distribution is easy in this case because it can be interpreted. So you can, for example, assume what was the earlier predictions or earlier survey results and get estimates, get it as a prior for this process. And this lecture should be available to you on Tuesday morning, and along with that, there will be certain new exercises to do on the GitHub in the laboratory part. So be ready for that, and hopefully there will be no problems for you. Sorry on this lecture we had a lot of interruptions here, so I hopefully added some of them, but it's night and kids and animals are rising. So have a good night